Marinus. I started this company called Aerial Imagery about a year ago. I did my master's in UAVs specifically related to wetland applications, but recently a lot of other environmental applications. Also want to acknowledge the University of Johannesburg. There's a few other parties also involved, partnerships and collaborations. I'm not mentioning them now, but if anybody wants interest in that, they can ask me afterwards. So just a short overview of the company, what we do. So we provide remote sensing solutions using UAV imagery specifically, and we're focusing RGB, which are normal digital cameras, multispectral, thermal, and LiDAR. So like I said, I did my master's degree, studies on this wetlands. We also recently started this year, I'm also a guest lecturer at the University of Johannesburg. So the honors students in remote sensing, we also do UAV since this year. I also did a number of local and international publications in this field. If you're interested, I can point you where to find them. So we say this technology is advancing quite a lot, and it's lightweight, and it's computer vision. Computers went so far, it makes this possible. And the interpretation analysis is good, but we do a trustworthy quality solution delivery. And then the products that we offer is mapping and planning. So we have a specific area that you need to imagery from. We can do it on demand as required. We do precision monitoring changes over time, and then also analysis, interpretation, and the research, which we're very big on. We completed 2 research projects, and we'll show some of the results in this presentation. So just the overview, that's the idea. All of these things you might be able to use a drone. Agriculture, construction, water resources, ecology, vegetation. We had a few applications on the moment. Fauna, which is difficult with overlapping photos, where normal conventional methods might still be better. Heritage resources, power line routes. I think there's a presentation somewhere later. Social application and visual impact assessment. We're going to focus mostly on environmental applications. So just to put some background to this, put some scene towards this. So time and budgets don't always allow for extensive planning and monitoring. Limited time is available for collection of data. It costs money, and on-site evaluation, the more hours and more persons involved, the more money it costs. And then also geospatial information available in South Africa. It's got it's not high resolution, it's limited. There's not fine details in those information necessarily. And accurate and relevant data is important to have a good understanding of a specific area that you're interested in, and to predict potential impacts and do assessment and monitor changes. And we also require more focused and integrated monitoring, I believe. Just to provide more background in where UAV fit in with a range of other technologies, you can see it's right in the middle of other technologies. I just want to put this pointer so you see there's UAV technologies. So the larger the area, you will go to normal manned aircraft, the complexity of the scene. If you go towards this slide, you can see the satellite with your manned aircraft going to a fixed wing and a multi-rotor. Multi-rotor will give you more details when there's real accuracy required. In terms of this, is a bit small in terms of cost. It's very well suited. It's close to normal ground surveys, and it's cheaper than satellites. It's a bit small to see on the moment, but overall it fits right in the middle, and for smaller spatial extents it's very well suited. Then types of UAVs, we use a range of UAVs. We tested a few one of the studies. We also compared for environmental mapping a multi-rotor versus a fixed wing. This is a fixed wing Skywalker that we used. Some of the research that we use, there's one of these examples, that side, if you're interested. It's a JACM imaging system which can be in the air for 75 minutes and cover about 200 hectares. And then there's also an example of this Raven carbon copter. And this is DJI Matrice, which is, they provided commercial equipment from China, which is very affordable and very good on the moment. Just going quickly through sensors. So RGB is receiving, it's your normal point and shoot digital cameras, is receiving a lot of attention, and the technology is under day getting better and it's very cost effective, and what you get out of it is just amazing. The thermal sensors is still not as you want to plug and play, and it's not necessarily giving you the results, but I'm sure we will get there. We're also busy for the last 2 years with R&D and thermal sensors. Multispectral sensors is currently very good. This is a mica sense which we also used for one of the research I'll show you later. Those things is available in the market, and you get very good results. Then there's a lot of focus on hyperspectral that will give you details of plant diseases, but it's still heavy and it reduces your flight time. But I think we'll soon also get a lot of different bands and available in the imagery for that. Then LiDAR, also very popular in the moment. There's a lot of LiDAR available. It's very costly to buy a LiDAR device. It will at least go over $1 million to $1.5 million. But it's a very good technology, and it's receiving a lot of attention worldwide. And then there's even guys that put a radar on a drone, but it's not a frequent thing. So giving you an understanding of what you really get, there's a 30 centimeter S3, which you can see some detail going up to a 5 centimeter UAV image. You see more detail going to 2.5 centimeter UAV. So you see there's quite a lot of difference in the imagery. This specific picture is quite nice because with low resolution of 1 meter GSD, there's a lot of features in that specific pixel. But as the resolution go up, it's only a few pixels, and you actually can identify even the colors correctly. So at the university, we worked with object and pixel-based classification now data in ArcGIS. So the amount of detail that you get out of there when you classify vegetation is amazing, but maybe now the challenge is it's so much data, it's so fine resolution, it gives you another problem again. Camille's and Krall case study. This is a case study which I did part of my master's studies 2 years ago, where we used RGB photogrammetry. I'm not going to explain the whole concept of photogrammetry in a moment, but if anybody's interested, they can ask me. Just the overview of the materials and methods that we use. So I am a wetland scientist myself, so we did first your normal baseline on-site evaluation study, and we compared it with results from the UAV, where we're trying to enhance the study. So we first do our baseline wetland assessment, you do your flight planning. In this instance, we also used a Trimble survey system, and we to get accuracy in the actual data. Otherwise, you will end up with 2 meter errors at least. And then we used computer vision software to process the imagery. And then afterwards, we did some editing and analysis, and a variety of different software applications for specific areas. We focused on hydrology, geomorphology, and vegetation, and also the delineation part of it. For example, here's your delineation. So the baseline delineation was your red line, and the UAV delineation was the blue line. In this specific area, the indicators of the swirl, there wasn't good indicators of hydromorphic swirls, so we used indicators of areas where water collects. So we did a flooding of this area in GIS, and we use areas to see where water collects, and even where the surrounding area where water will actually flow towards the lower area. Some other methods to actually say this is actually where the wetland was supposed to be, and it increased by 3 hectares in this instance. Here's an image of the same study area. We did a drainage network of the entire area where all the water will eventually meet the mainstream, and it will even show small profile changes if there's a gully or an obstacle where the water will actually flow around to join with the rest of the stream. This is just a normal orthophoto. This is actually kikuyu grass, which is overgrown on an earthen dam. From the imagery, you would be able to see most water actually flow around the dam. There's a lot of information in terms of the erosion gullies there. And then you go to a 3D model of the digital surface model of the entire area. So you can clearly see and understand, almost like a bird's eye view, where is the interruptions in this wetland, all the earthen dams. All those areas which you see here is pragmatis. It even captured nicely in the 3D information. And then you can see all the interruptions in this line showing you the actual delineation line. You can do measurements after your site visit, after your erosion gully. You can determine the depth. You might even be able to determine the volume. We did it. So there's a lot of information in this. Then you can go to fine-scale vegetation mapping. So this is all your pragmatis, for example. You can go even further in a point cloud. There's all the different points. There's almost 700 points per square meter that we got from this imagery, from the photogrammetry. You can determine the heights of those pragmatis over time. And then you take a piece of those pragmatis out, you zoom in even further, you see starting from 0 to 2.5 meters, you can determine where the heights of those vegetation is. Another case study, similar study area, which we did actually, the case study more involved of comparisons of a multi-rotor with a fixed wing. What I'm just showing you, it's very promising in terms of erosion gully monitoring. So we'll end up with something like this, so you can do frequent monitoring over this and you will see changes. You might be able to see where the sediment is going, if it's going worse or not. So this is a profile through the head of the gully. You can even see here the small gully which is joining up with the main gully, and it's 14 meters. This is about 2 meters, 4 meters in the width in that area. So there's a lot of application for monitoring of those type of things. I'll get to more information on that later. Another case study which I presented also overseas a while ago, 2 months ago, which we did this year. The study was also published if you're interested. We also did a wetland, so we did some integrity assessment. Is there a fast way to do integrity assessment with multispectral UAV imagery? So in precision farming, there's a lot of applications. They define management zones in a field, in maize maybe. They say this is a problem area. We have to give more water or more pesticides or more fertilizer. So we thought, can't we use it for wetlands as well? It's a very fast method. So can't we define management zones or see changes on it? So limited research in wetlands with multispectral imagery have been taken place over the world, although there is a few. So the materials and methods that we used this JAG-M imaging system, which can fly for 75 minutes and cover 200 hectares. We also used ground control because it was a study that we want to publish. We used the Mica Sense Red Edge camera. The flight once was about 26.1 meter apart, so it captured 5 images at every location. It equated to about a 70 forward and the side overlap. So we did it very early in the morning, 28 minutes, and it was about just 3,815 images. So we also used radiometric calibration to make sure that the data is correct, that you can actually compare it over different times of the year. If you don't use radiometric calibration, the illumination, all things you can't really compare, especially if you've got vegetation indices that you work out. We actually tested 3 different software applications, Atlas, which is a cloud platform, Pix4D and Photoscan, and we actually compare the results. And then we did analysis and interpretation, a lot of empirical computation, including the NDVI, which provided us a lot of answers. So we use wet health, rapid on-site assessments, and then the interpretations that we made was actually based on actual field knowledge. This is a 5-band orthophoto. I have all the bands available just to give you an idea what can you see from this. So this was all your black wattle also and silver wattle and different wattle species. This area, which is pinkish color, was all your wetland vegetation remaining in the specific area. This area was previously a sand mining area. Now I can clearly see the erosion in the areas that is still largely affected by this anthropogenic disturbances in this area. Just results in terms of the different softwares. So the Atlas and the Pix4D was very similar. The big reason for the big difference was that at that stage Pix4D didn't have any radiometric calibration that you can import into the softwares to make sure that the illumination and the sunshine is actually measured correctly. So we actually ended up using Pix4D because Atlas didn't support ground control for correction. With the Photoscan software, for example, wetland areas was shown having a low vegetation index value, low normalized vegetation, different index value, which is actually supposed to be live vegetation at this stage, although it was going into dormancy at that specific time of the year. Okay, what we did then, we actually divided it in 10 classes. We used an optimization method, so divided the NDVI in 10 different classes. And then to see what we get out of it. So the low values, the disturbed, corresponded with mostly the disturbed areas, as you can see, earthen dams, all the areas where the erosion was, previous sand mining areas, deep and shallow flooding by dams, areas of infilling, for example. And then number 2 shows a correlation, the intermediate values, with include wetland and grassland vegetation mostly. At the higher end of it, it started to have kikuyu grass that was in a bad state, but was dying, and seasonal weeds eroded kikuyu grass. But mostly this was wetland vegetation and grassland vegetation. Going into your higher values, it picked up all the kikuyu grass and all your alien vegetation. Clearly, this entire area is a kikuyu planting from the farmer. So we would be able to very accurately map these areas instead of field observations using this technology. The next slides, I'll present you some. Interesting in this area, this farmer used fertilizer for the kikuyu plantings, and there was a fertilizer like an erosion channel where all the fertilizer washed from this area. This is the area where the most vigorous growth of kikuyu and alien vegetation was taking place. The results, so on-site evaluation was difficult and time-consuming. So UAV multispectral NDVI integrity assessment provided significant increase in accurate refined results. Disturbed areas and areas with erosion was overestimated, for example, with field evaluation. Alien and invader vegetation was underestimated. It was possible to accurately map the kikuyu grass, and minimal human disturbance was underestimated. So, overview of the study area, you walk around there, and as a wetland specialist, and you make your assumptions, and you say, okay, but you don't count all the different areas in between, which is not necessarily disturbed, and the areas which does have alien vegetation. We plan to extend the study to do it over different periods to see if the vegetation dynamics still correspond with these values. It might change over seasons, and we might not be able, or we will still be able to do the different distinguishing between the different classes. Another case study we're currently doing with the Department of Environmental Affairs, it was just 3 weeks ago. It's part of the Colburn wetland system. So we do a verification of the rehabilitation interventions and see if it's actually working, and is it still intact? What is happening to those areas? This is the orthophoto. This is a digital surface model still with all the vegetation. And then here's a terrain model where we take all the vegetation away. There's some contours here. So what we actually did is we take all this vegetation away, and then you can see the flat areas. There's a key point installation gabion where we actually re-wet this entire area, so you can see this flat areas where the re-wetting is taking place. And then you can even in fine scale see the vegetation and the heights of those Pragmatis reeds in this area. Here's the channel coming in, and where the water actually go. This is a railway track splitting the specific wetlands in two. That is the gabion where where they actually restored the functionality of the wetland to re-wet it. And then there's another gabion where you can even see the sediment in the water and the sediment build up in the specific area. So in rehabilitation, for example, the applicability of this, you integrate it with your on-ground observation with UAV spatial remote sensing products. So effective monitoring during establishment phase, demonstration of the progression of your rehabilitation, interpretation of monitoring plot data, reduce the need to make inaccurate assumptions of rehabilitation landforms. You can show your client or everybody who's spending money on this is really what's happening. It improves your quality on ground metrics, for example, direct measurements of tree density, erosion and vegetation cover. In terms of rehabilitation interventions, it's all early warning systems. It will help you with adaptive management, improve monitoring and evaluation data considerably, and save on maintenance cost due to detailed monitoring. Just quickly, the outlook. This is my last slide. It will enable you for precision planning and monitoring. It will make you better understand your project, and it's a more accurate estimation and prediction of impacts. And there is a limitation. It's better for smaller applications. You will not necessarily go over 10,000 hectares, which is already fairly large. And yeah, more effective management and conservation of areas, and it helps you conserve your ecological infrastructure. And you can use it throughout your planning, and you might be able to use the same data for engineering applications all over a project lifespan. I hope it wasn't too much information. Thank you.